would have went off researching for that.
That's right. Yeah. Okay, so I'm going to give you the final equation. Okay, but I just want to be clear that it's not curriculum. Okay, I just want to show you the final equation that Planck came up with to model the intensity. Yeah, so the intensity or power output of a black body as a function of frequency and temperature. That's E. No, that's E. That's the constant, the mathematical constant. Is that called Euler's constant?
Yeah. Euler's.
What's K?
Is it Euler's? Yeah. It's Euler's. I don't know why, but it's Euler's.
What's K? This is the same.
K is Boltzmann.
Boltzmann.
H is Planck. Yeah.
Can we just
Okay.
put the bottom that's the negative one? That's hard to write.
What's that?
Put it just to the negative one, just because that's hard to look at.
Yeah, I guess you could have. Yeah. So I just wanted to show that, like, this was a monstrous amount of work that he put towards creating a better mousetrap, or a better light bulb in this case. Right? And he did. He was able to apply this to making a better light bulb, but though his whole discovery of, like, reinventing the black body curve was sidelined. It's like, oh, here's my better light bulb, but in doing so, he really completely renovated physics. Okay. So that's the end of the board note for you guys. Because what this brings us to now is the start of the actual IB curriculum, where we're getting into the verifications of Planck's constant. Okay, Einstein took over very shortly after. Einstein was in communication with Planck. They lived in the same time frame. This is all early 1900s to 1910. They were in communication after he saw this awesome equation. He wanted to verify it in other ways. And the way that Einstein verified it is through the use of the photoelectric effect. Could you hand this out, including one of this PC? And I'm going to set up a demonstration of the photoelectric effect.
That's why we have a microwave.
You guys can all see this.
Stein's Gate. It's an anime called Stein's Gate.
Stein's Gate.
Yeah, it's where he puts like a banana in the microwave to verify that like the molecules in it changed like.
What's a
It was like they changed like the position like weirdly, and it eventually like the banana traveled through time. Like a weird quantum effect. It's really weird.
I want to know more about that. Okay. Could you guys just in case? I don't think so. But could you guys? Actually, Josh, can show
It's me shaking up.
No, it's fine.
It's been 6 days.
You ready? Come on, do something. Oh my god. Okay. That's neat, eh? That's the photoelectric effect, which we're going to talk about in a second. Oh yeah, I got one more there.
Does anyone have like a slow motion camera or wait? Is it ruin it?
No, when you go, yeah, they completely prize the.
Oh, that was cool.
I'll show you one more time.
That's like Tron.
Yeah.
Yeah. They stick their discs in the microwave.
Wait.
Okay, Josh, lights please.
Is that just your?
So what's happening there? Shh. Oh yeah, I'll pass them around after. What's happening there is the high energy photons of the microwaves are striking the metal surface of the CD, and they're ejecting electrons from it. Okay? Individual photons, remember this is a new concept, individual photons of light are striking the metal surface of the CD and ejecting electrons off of it. Okay? It's literally just a... What's that? No, your food's fine. It only works for metals. Unless you're eating some weird stuff.
That's why you don't put tinfoil in the microwave.
There's zinc and iron.
Yeah, but it's not that, and there's such small quantities, it's not going to do anything.
Don't put your nose on fire.
Potato, my mom was like, music out. Microwave. That'd be a great way to like.
Yeah, it doesn't smell too good.
Your spine.
Oh, that's what happened with the cooler.
You guys ready to go? Yeah. Okay. So let's read here together. So one of the fundamental principles of quantum mechanics states that the building blocks of the universe, Rob, exist and move in discrete states. Okay, so a discrete system is one where only certain values can exist, as opposed to a continuous system where the entire range of values can exist, limited only by the number of decimal places. So, I mean, a real-world example of a discrete system, number of cars on a highway, when you roll the dice, you're not going to randomly get 1.25, hopefully. Yeah, so anything that has like a counting or a whole number integer value, okay, that's a discrete system. As opposed to time, right? When you measure time, if you're only limited by the accuracy of the stopwatch. Okay, that would be a continuous system. Yeah. I'll just intro the photoelectric effect, then we've got a demonstrate an interactive simulation. Okay, early experiments in the 1870s by Heinrich Hertz showed that when light strikes a metal plate or a photo surface, the light caused the electrons to move. If the metal plate was set up in the form of an open circuit with a parallel plate type apparatus, which you can see on the right-hand side, the electrons would be ejected from the surface of one plate and attracted to the other plate through induction. The electrical characteristics, like voltage and current of the electrons, could be experimentally measured through the use of a galvanometer and a reverse polarity battery. Okay, let me show you what I mean by this simulation.
Probably not there.
Oh, a galvanometer is just a small ammeter.
Oh,
That's it.
so wait, a Galvin is a measure of current.
Yeah, an old measure of current. Yeah, it's not used anymore. No, it's just amps.
Oh, okay.
Yeah.
So we could use an ammeter for this these days, or?
It's such a small current, they still call it a galvanometer because it's like microamps, like millionths of an amp.
Oh, okay.
Okay. So let's see what happens here. Anybody want to come up and play with this? Okay, come on, bro. Okay, turn the light on. Turn the intensity up to, let's say 100. Oh, are you kidding me? Oh, I'm sorry. Hold on. No. You're able to write on it though. That's nice. Rob, apparently my the interactive part of the smartboard is not working. Here, I'm just gonna turn it on for you.
Okay.
Here we go. Wait, no, don't click. Don't click.
Oh, sorry.
Okay, I want to show photons. Show photons.
The options.
Options. Show photons. All right, Rob, what do you see? What's happening here?
So, flashlight with almost UV light. It's hitting this piece of metal right
Okay.
here. And
What are the other things coming off of that metal?
The electrons.
Good.
They're, I guess, are they high energy electrons?
Good. Yeah.
And they're being sucked up by that guy. Or
That's right.
absorbed.
Close enough.
Yeah.
So why do you think they're being attracted to the second plate? Yeah, the potential difference. That battery is really. I'm sorry, I can't. It's usually all. Well, I'd have to reset my computer.
Is it
when
like
glitches
this? Do I have to?
No.
Is that something with it?
No, it has. When it glitches like this, the only way to fix it is to reset my computer, and that takes like 5 minutes. So, Rob, thanks for coming up. I would have had you play with it some more, but it's yeah. Because we have a reverse biased battery in here, so it's creating a positive charge.
Do we have a normal battery in there?
Yeah, it's a normal battery, but it's like
bias.
the opposite way. Instead of generating the current, the battery is just providing a positive charge on this plate. No, not quite. And that's attracting the electrons to the other plate. Okay.
Yeah, what happens if you increase the voltage of the battery?
Okay, that's a good question. Let's see what happens. Okay, so if I increase it in the reverse biased way, okay, it just attracts the electrons faster.
Doesn't change the current.
But
Increase the.
that's right, it's just increasing the attraction, right? Negative electrons are attracted to the positive plate. And then we can tell what voltage those electrons are by stopping them, by flipping the battery. Okay, if we flip the battery so that it's a negative charge, it's pushing the electrons back into the original plate.
So technically, can you freeze the electrons in the middle?
No.
Just keep flipping the battery.
No. I mean, it's in a more advanced system where you can change the voltage.
We can have it so that they almost make it.
Position of the electrons.
Okay, so if you tune that battery to where it's just repelling the electrons, then you can tell what voltage those electrons have as they're being ejected. Now, here's where, again, classical physics predicts something that is not observed. What classical physics predicts is that as you increase the intensity of light, okay, or let me start with low intensity light. Classical physics predicts that as you increase the intensity, the energy of the ejected electrons would increase. Makes sense, right? More incoming photons or more incoming light means more energy to eject the electrons from. But that's not what happened. Look what we're seeing here. I turned down the light bulb, okay? It's still the same color. I turned down the light bulb. The only thing that's different is what? The number of electrons, okay? Now if I put my battery back to the opposite volt, we can actually see that the current is what has changed. The stopping voltage was not affected. So the current is changing by changing the intensity, by increasing the intensity. Okay, you can see I'm increasing the current, but I'm not. That's right. I'm not changing the voltage that it takes to stop the electrons. Okay, and that was another thing that broke classical physics. And we're going to see when we go back to the note what the predicted versus actual values for the graphs are.